The complements of the components of a vector. Sorry, the complements comes next. So what vector components are made up of the x and y components. This would be called component form in math classes like pre-calc. The terminology would be vector r is equal to x comp plus y comp. It's going to be the same as a equals ax plus ay. So what does this mean? So let's take something like square root 2. And let's say that this is... I can't draw a straight line. Let me just make it smaller so the line can look straighter. That means this vector has a magnitude of square root 2, which can be written as plus 1, or I believe in component form it'd be 1i plus 1j, because it goes 1x and then 1j value. So this is 1, 1. And that's essentially the same thing as denoting the vector's magnitude and direction, which would be 45 degrees if you learned your special right triangles. So that's the logic behind there. So simply it's saying that you can break a magnitude and direction into x and y components, which will be a lot easier in the next one. As we go on to the next slide. So it is often easier to work with scalar components rather than with vector components. Scalar components are just a direct number like plus or minus. So like in that example there, we have a square root 2 and we have plus 1 minus 1. It's easier to say rather than a vector of magnitude of square root 2 going in the 45 degrees direction, when we could just say it goes plus 1 minus 1, or plus 1 plus 1. Sorry, I don't know why I said minus 1. Because it's going 1 to the right and 1 up. So it's easier to say it like this, because then we can just add vectors like that, which we'll get into in 1.8. But you'll have to convert it into scalar components so you can add x and y values, and I keep clicking that. So let's give a specific value, an example, and we'll do a 30, 60, 90, simply because those are my favorite triangles. It's 60 here and 30 here. And we'll do x, y, and r, so kind of like polar form. If we had to, let's actually assign values to here. And I know how to assign values because it's a special right triangle. So let me just erase this and try it again. So what we'll do is 30, 60. Oh, sorry, that's actually wrong. It should be 60 and 30 here because it's corresponding. Okay, so let's assign this as 2, let's assign this as 4, and we'll assign this as 2 square root 3. Now, instead of saying scalar form of magnitude 4, or a magnitude of 4 going 60 degrees from the east to the north, we can instead just say 2 to the right, 2 square root 3 up. So that's the logic of scalar components, which is way easier than using the magnitude and the angle. Unit vectors are scalar components but scale relative to hypotenuse. This is all just proofs, I guess, or logic. So let's come over here. So when we have a vector, and let's say we have a vector of 1, and actually let's make it even better. Let's use square root 2, just so we can denote these sides as 1, because that's how it works. If we want to scale this up, so if it's square root 2, if it's a magnitude of square root 2 per every second passed, that means that we can denote this as square root 2. So if 2 seconds has passed, then that means we have to add another square root 2 because of the vector transformation, or because 2 seconds has elapsed, and this is per square root 2, so the magnitude gets bigger. But notice what? We can also use this relative to a similar right triangle, because as this gets bigger, nothing actually changes. Only the hypotenuse height changes. All the angles stay the same, which means that this triangle is actually similar to this triangle. So what can we do with this? Well, now what we can do, because these angles will always be the same, now what we can do is we can scale the x and y components relative to the hypotenuse. And how do we do so? We use something called a unit vector. And a unit vector is simply the x and y components divided by the magnitude. So here it would be 1 divided by square root 2, which I guess you can rewrite as square root 2 times divided by 2. And square root 2 divided by 2 for the same here. So this means that per height of magnitude, or how many seconds passed, you can simply scale it up infinitely. So if it's 2, then we can scale it up infinitely. But now the hypotenuse is scaled at 1, square root 2, which is the same exact triangle on dimensions here, just with a shorter hypotenuse, with a hypotenuse of 1, so you can scale it up infinitely. So we can do square root 2, and scale it up infinitely. Technically, you can just break it into its component form and do it that way, but it is slightly a little bit harder that way, so they'll simplify into a unit vector. So let's read it here. A unit vector is, regardless of the hypotenuse length, all triangles made using the hypotenuse will be similar, and therefore a ratio can be set up. So in simpler terms, they are vector components in regards to x and y that show the relationship. So for x, it will be adjacent divided by hypotenuse, because that gives us how big the adjacent is relative to the hypotenuse. And for y, it'd be opposite divided by hypotenuse. That means we can find the adjacent length, since we can multiply that by the x component to find what the x value is of the vector. So let's even simplify this. Let's simplify this even further. I'm going to make it super small. That way it's a little simple. Little simpler. 1 square root 2. As we scale this up and we multiply it by 1 square root 2, 1 square root 2. We notice here we can just we can find the x and y components relative to the hypotenuse. So if the to do so, we convert it to a unit vector as we've explained before. So this is the unit vector for 1. So it increases for every length of hypotenuse 1, we increase the x component by this big. So that means that if the hypotenuse is 1, it would be 1 divided by square root 2 and 1 divided by square root 2, which are the same exact dimensions as this. This one's just slightly bigger because the hypotenuse is slightly bigger. So what actually happens is if we have this relationship, then that means depending on the length of the hypotenuse, we can denote how big the x value is. So if the hypotenuse is square root 2, then guess what? We have an x component of length 1. And if the hypotenuse is like 4, which is square root 4, we have square root 2, and that will be the length of this, which is really easy and simple to understand. So that's the logic here. And resolving vector into its components is the same thing as vector components, where we can just break it into x and y instead of denoting a vector in terms of its magnitude and angle of direction. So that's the logic there for 1.7.